Hello everyone, it's Wisteria. I welcome you all to a new video lecture of the recommended book series. The book which I am featuring today is the Thermal Physics book by Kirk, Bansal and Ghosh. As for today, the topic will be statistical mechanics. So we will be starting the video from the chapter 12 of the book, which is basically the starting chapter of statistical mechanics. So without further ado, let's get started. So as you can see, this is the book by Garg Bansal and Ghosh. And here's the chapter, the first chapter of statistical mechanics. As for the number, it's the 12th chapter. So let's dive into the book. Here in the introduction part, there are not so many important lines or things that we need to know. The only things that we need to know is like this part that says that in kinetic theory, one applies in kinetic theory one applies the laws of mechanics to individual molecules of a system, while in thermodynamics one deals with directly observable macroscopic properties without any reference whatsoever to microscopic structure. These lines gives us a basic knowledge upon what the thermodynamics works and the kinetic theory works. The kinetic theory is called to be a deterministic theory or the classical theory, and the thermodynamics is the phenomenological or the observation based theory. But due to some reasons that we may discuss a bit later, none of these theories are completely workable. In some cases that we need them, but they can't give us ideal laws that governs a system. Then why statistical mechanics? In statistical mechanics, we deal with a system that have a large number of particles, such as 10 raised to 25, and the attempt to relate the macroscopic properties in terms of statistical averages with no reference to the details of molecular motion per collision. Thus, we are trying to figure out the laws that governs the system by statistical averages, statistical methods, without any reference to their individual molecular motion. So, though we have a large number of particles, but we are not dealing with them individually. We are taking them as a whole and doing some statistical works to understand how they work individually. While in kinetic theory, we were trying to deal with every single one of them by applying the classical theory on individual particles. And in case of thermodynamics, we were like watching the system from some frame of reference and trying to understand how it is working. In the both cases, except of statistical mechanics till now, we get errors that lead us to wrong rules, assumptions that might not work at all. So for correcting them, we started this new very branch, which is known as, shouldn't say new, it's very old after all, this branch, which is the statistical mechanics, where we deal the problems with statistical approaches. As for the definition, we can say that statistical mechanics is the probabilistic approach. It is the probabilistic approach to understand the equilibrium properties of a thermodynamical system containing a large number of degrees of freedom. Throughout this course, I will tell you guys about this in much details, but for now keep it a little brief. So after this, in this page, there's not much information we need to know. So let's give heading forward. But you guys can read the parts given below if you guys have the PDF or have the book as well. You will be fine. If you want the link for the book, that will be in the description below, so check out. Okay, now here there are some things that we need to know. That is, you can say that when a system consists of a large number of identical particles, one can use the observed behavior of the individual element to predict the behavior of an entire system. Conversely, the probable behavior of individual elements can be obtained from the observed properties of an entire system. This is how the statistical mechanics works. This is the basic outline of statistical mechanics. We must know that. So after this, we have got some problems regarding basic probabilities. We will not be discussing them in this very lecture series. That I will make another series containing the problems. I may discuss them there. For now, let's stick to the theory for now, or maybe later, after completing the theory, we may dive in the examples and the other problems we have here. So now comes into the space and the quantum states. I guess before we dove into the space and quantum states, we must do some basic information. We must get some basic information about the previous things. So I have a note. Let's see them. So I said that what is the definition of statistical mechanics? It is a probabilistic approach to understand the equilibrium properties of a thermodynamical system containing a large number of degrees of freedom. So this is the very definition that defines what is the statistical mechanics. Now, a lot of people may think, why probabilistic approach? We could have taken some another mathematical ways like set, or some other theories like number theory or fractals, complex theory, anything else. But why probabilistic approach? So the answer is, I have told you guys before as well, but let's look into again. In statistical mechanics, we use probability to guess the laws that governs the system of our interest. In case of kinetic theory of gases, where we try to apply laws of mechanics on the molecules by considering some assumptions, the assumptions of the kinetic theory, of course, which is not appropriate in finding the laws, as it is deterministic. Now, what is the problem if it is deterministic? As we know, in deterministic way, or the classical way, we must know the initial conditions of the system. Unless we can't use the boundary conditions, we must know the initial and the final condition of the system. But let's say we have a system that contains a large number of degrees of freedom, means a large number of particles, and when we start observing the system, it's not like that system start evolving at the very moment. It might have started a very ago, but not that moment. So we don't know, we don't have any information about the initial conditions. Thus, we can't use the deterministic approach at all. And in case of phenomenological approach, you may say that, oh, okay, this is a good approach, as the laws we get from the phenomenological approach seems to be right, but they are not. Why they are not, I will be discussing that in the next section, but not now, so please wait for along. Now, what is probability and how it works? We don't need to know the great deal of probability at this moment. We just need to know the basic formulas of probability and how it works. So let us have a system that contains n number of particles. Now consider all probable states as a set. That very set we now call as the state space. That means that we have a system that contains n number of particles. Now, as we have n number of particles, they must have a lots of states for them. Every single particle have a literally infinite number of states. Now, if we take those all states as a set of that system, then that set will be called as a state space of the system. Now, among these states, the ith state would have the probability of occurrence pi is equals to ni by n when n tends to infinity. This is how the probability is defined. Now, let's say we want to find the probability of the ith state among the all states of the state space we have. The ith state's probability will be defined as pi. And how? Let's say the ith state occurred ni times among the n number of particles. We have ni ith states among the n particles. Total number is n. Among ni are ith states. Then the probability of ni will be p of I is equals to ni divided by n when n is very, very large number. So we say it tends to infinity. Now the expectation value of some quantity related to this related to the system, say f of x, will be defined as summation of f of I p of I. These are some mathematical formulas that we must need to know. So keep memorize them for now. We will be dealing and discussing about them later in details. Now, as for today, we will be finishing this chapter's introduction by understanding how we deal with systems in statistical mechanics. After that, tomorrow, I shouldn't say tomorrow, the next video we will be starting from the phase space and the quantum phase space and the quantum states given here. That will be the next section. For today, it will be finished with the introduction part. So what is that? Okay, so how we understand a system of statistical mechanics. Let's say we have an object that can change its color. Before I go into this very thing, I must tell you guys that this very example is not my own. I learned it from the video lectures of Stanford University. If you guys do want to watch the video lecture of Stanford University as well, I will give the lecture link down below, so don't forget to check it out. Okay, so let's consider we have an object that can change its colors. Let's consider an object that can change its colors over time. We want to find the laws regarding the object, that how the color changes over time. So we can write this phase space as S is equals to red, blue, yellow, green and orange. These are the states that the object can take, the color can take. The color can change in between these only values. It can just be converted into crimson or something like violet out of nowhere. If these are the states, the object must be in those states in some certain time, not anything other than these. So now if we start from a random moment, as we know that in case of the system that we study in statistical mechanics, we don't know the initial condition. So if we start from the random moment here as well, we don't know the initial moment, thus we can't use the classical deterministic approach here as well. We don't know if we start from blue, was there a first moment before blue which was red or which was yellow or anything else, or blue itself is the initial moment. We don't know, we have no surety. So from the checklist, classical deterministic approach is out. We can't use it. Now, in case of phenomenological approach, what's the problem? So, in case of the phenomenological approach, we observe the system for a long time and then say how it revolves. Like we saw that, say we started with yellow, the block which was at the yellow state at the beginning converted into green, then orange, then red, then blue, then yellow, then green, then orange, then red, then blue, then yellow, and keeps doing the same. So we get a revolution cycle, a perfect chain in which it is changing, which is red, blue, yellow, green, orange. We are saying that red is the initial one, or as it is revolving, orange could be the initial one. No one needs the initial situation now. We just know how it's revolving. So everyone will say, oh, okay, it's good, no problem. But who know? Can anyone give any assurance that this very cycle will be the same after 1 million or 1 trillion times of the revolution? No, no one can. No one knows what will happen after that, as we cannot observe till then. Thus, we need probabilistic approach. All the states are equally probable here. They last for equal time. That's the basic concept of statistical mechanics, or you may say the basic assumption. If not, we need to edit the formula as for that. But for the simple case here, we will thinking that each state remains for the same instance. They last for same interval. Now, in that case, they will have the same time of interval to be in some state. So we can say in that way that all the states are equally probable. All of them have the probability 1 by n. So the rule, the law of the system is now all the states are equally probable with the probability of a certain state to be occur as 1 by n. This law is not something like a revolution. It's not telling us that it is revolving like red, blue, yellow, green, orange, or red, yellow, blue, green, orange, or red, orange, green, yellow, blue, or anything else. No matter what is the revolution, this very probability will never change. So we can say now that it is nearly unchangeable for no matter how the system is revolving. This is how the statistical mechanics works. It gives us an alternative way to understand a system, a completely different way other than the deterministic or the phenomenological approach. Now, from this discussion, we can conclude that probability is related to conservation laws for some quantities defined by some state. The probability also tells us about how much time do we spend in the certain states. So if you like this video still now, do comment, subscribe, and watch again. Share to your friends, and don't forget to like. For today, we will be finishing the video here, and for the next video, we will be starting the the phase space and quantum states. Till now, you've understood the concepts that has been told in between these very introductory parts. Hope you liked it. So, goodbye for today.